Howdy. On today's video, we're going to build a one-to-one Balun, put it into a small enclosure, and create a fan dipole. This will be a dual band 10 meter, 15 meter dipole. So let's get to it.
Okay, before we get into the actual construction, let's take a look at what we're going to build. So we have a FT240-43 core and bifilar windings. Basically, these are parallel 16 gauge Teflon coated uh, conductors. Basically, the 16 gauge is going to give us the capability of running 500 to 800 watts, and the Teflon coating has a very, very high melting temperature. So, all in all, it will make for a pretty stout one-to-one Balun. So, we're looking at 12 turns going in this direction and 12 turns going this direction, and the windings need to be really flat up against the core, and we'll see that in just a second. So one set of windings of like some color, in this case I used orange, they're combined together, and that is your terminal 1 for the left hand element, if you will, radiating element, and the right hand element is connected to terminal 2, and that's these blue windings. At the SO239, we're going to essentially do almost the same thing. The center pin goes to the orange, or color number 1. It doesn't have to be orange, but it's convenient to have two different colors so you can tell them apart. And the blue is connected to the one of the screws on the SO239. In order to make this even more stout, you could stack cores. Like this is a single FT240-43. If you were to stack two FT240-43s and use something like medical tape or any kind of like gaffer's tape, if you know what that is. Just a couple of 3, 4, turns of gaffer tape around here to keep the two cores tightly together, and then wrap your wires around that. That just makes it easier. It also gives a kind of a no-slip surface for you to wrap your wires around. Yeah, so basically this is the basic design. This is the circuit diagram, essentially showing that it's 50 ohms on the input, it's 50 ohms on the output terminals, and yeah, so we'll put this together now. Let's go to the bench and start working on it.
All right. Through the magic of television, we are already done. So there's the connections down here. I'll tilt the box up. Basically, I combine the reds and connect it to the center pin. Combine the greens and connected it down here to one of the screws for the SO239. At the top part, again, combining the reds and the greens, and the reds go over this piece of wire to this terminal, and the greens go to this piece of wire over this terminal. And we've got a nice little cover for it, and so we're done. Next is to put it on a pole and attach some radiating elements to each screw and string those radiating elements out and connect a coax. So we'll get that up in the tree and we'll start testing.
Before I get to adding elements and hanging this on the Dipole, I wanted to do a little quick analysis of the performance of the toroid balun itself, the one-to-one balun. So what I did here is I added 50 ohm uh, resistance to the terminals on the dipole side of the balun, uh, and connected it up to a spectrum analyzer. And this is the results. We're looking from 2 megahertz to 50 megahertz. So 2 megahertz is on this side, 50 megahertz is on the right side. And we can see that on the 20 meter band, it's about a 1.2 to 1 SWR. On the 15 meter band, we have a 1.3 to 1 SWR, and at the 30 or 20 megahertz, 28 megahertz, 10 meter band, it's a 1.4. So this is somewhat typical of a 1 to 30 megahertz balun. So I'm pretty happy with that. It means that the balun is working correctly across the frequency band, the frequencies that I'm interested in. So now we can go ahead and start figuring out lengths of radiate lengths of elements for the radiators and connect them to the terminals. Okay, so as far as figuring out lengths of the radiating elements, I've selected 3 websites that you can go to pick out the values that you need. This one is at West Mountain Radio. It's a dipole antenna calculator, and it gives you a rough guide of where you should start with your lengths of radiating elements. So you can put in 21.2, that's 15 meter band, and it will calculate for you, well, a leg, one side should be 11 feet and a half of an inch. Assuming that's a straight flat top dipole. If you do an inverted V style dipole, there is a slight change in the element length, and that's basically because of there's also an impedance change or SWR change if you start bending the legs of the antenna down towards the earth. The earth has a slight effect on SWR. So if you continue down the West Mountain site, you actually have some measurements that are already pre-done. So 11.04 feet per leg for the middle of the 15 meter band. And if you were to do a 10 meter band antenna, approximately 8 feet per leg, so 8 feet on each side. For a 10 meter dipole. So let's also, I wanted to show you this site. This is 66pacific.com. They have a similar calculator. You put in a value like 21.2 megahertz. So this one's also coming up with about the same amount for each element. So 11 feet and a half inch. For the elements here. It's also a good site. And then the one I've been using, because mine will be somewhat an inverted V, so what I did was I'm over here at m0ukd.com, m0ukd.com. He has a lot of great calculators on his website, everything from quarter wave antennas to dipoles to inverted V's to base loaded antennas, uh, or coil loaded antennas. So good amount of different calculators on this site. So in this particular one, you'd have the option of uh, picking how much of a slope each leg will have, from like 30 degrees from horizon to the top of the leg. So if you're looking at the end point facing the antenna, what's that slope going up to the center support? So you can have a 45, which is essentially would be almost like a triangle, a right triangle at the center point, or the feed point. In this case, mine's close to a flat top, but more of an inverted V. So almost exactly like this diagram, maybe not so much of a slope. So this is a great site to use for that. And so if you pick something like 30 degrees, which is this angle right here, and you pick 21.2 and you hit calculate, you're going to get some slightly different values than you would normally get for a dipole. So in this case, it's saying 10 feet and 8.5 inches. And I found that this is more close to being accurate when doing an inverted V versus a flat top dipole. The fact that we're taking it into account the change in SWR for an inverted V kind of situation. So it also gives you a minimum vertical height. I think that has to do with the endpoints. So each endpoint of the V should be supported by about 6 feet off the ground. And then this would be your horizontal spread based on the angle that you picked and the lengths that it's seeing. So it's already figuring out, well, you're going to need about 19 feet of horizontal space on your property in order to erect this antenna. And it also throws in some straight dipole information. This would be the flat top value, 11 feet per section per radial element. So yes, I like using this site because you can say, I have almost like a 45 degree angle going up to the center feed from one of the ends, and then you hit calculate, and now we're down to something close to 10 feet and 6 inches. So yeah, I like this site. This is the M0UKD site. And definitely has a bunch of different calculators, pretty cool stuff. So the value that we are going to use for our testing, it will be this. I will pre-cut some elements, leaving a little play. When you make your elements, always make them just 6, maybe even 8 inches longer than you really need, and fold that back and just wrap it around the wire a couple of times and then secure it in place. That's what I've been doing. That way you get the ability to make it a little bit longer, make it a little bit shorter. Check it out on the on a VNA, your nano VNA or whatever you might be using to measure SWRs on your antennas. That gives you the ability to go up and down depending on your installation characteristics, depending on what's in the environment around you. Maybe you've got a garage nearby, maybe you've got an RV, maybe you have some chunk of metal like a car that normally sits right below your antenna. It's going to vary the tuning properties of the antenna, so give yourself some room to make those changes. Definitely make it 8 to 6 inches longer than you really need, and then just fold that wire back. So that's what we're going to do here. We're going to start cutting 10 feet, roughly 10 feet, 8.5 inches, and see where we are on the V&A. Okay, here's the Balun installed on the post. It's on the side of the carport here. I got an element right here that's bouncing back and forth. That's the 10 meter element set, and then right above it is the 15 meter. There you can just see the insulator right there going to the Balun. So currently have two element sets connected to the Balun, and then a coax cable that's running all the way down and around and into the shack. And we'll go in there in a second and take a look at it on V&A. Before we head into the shack, I just wanted to go over the foldback that I was talking to you about. As you can see in this insulator in the center of the screen, the wire's coming in from the right, and it goes through a little strain relief buckle and then gets folded back onto itself, and I have a little piece of electrical tape that's somewhat coming undone, but basically it's to keep the foldback wire attached to the original wire. There's the Balun way over there, but and on the left hand side we have polycord going down to the ground. But that's essentially what I was talking to you about as far as leaving some extra room. It's okay to make it 6 to 8 inches long. Just fold it back on itself and you'll be good to go. All right, we have a Nano V&A. This is actually the SAA2N. I like this one because it's got a metal case and it uses standard N-type connectors, very heavy-duty connectors. They're not going to break. For that, I have a N to SO239 adapter. I'll just attach it to here. And we'll connect up our coax coming from the fan dipole antenna. And currently we are sweeping from 3 megahertz to 30 megahertz. You can already see right here, this is the tuned part of the antenna for 15 meter, and the marker is currently right now at 21.360. So I'm going to move, there's the marker right here. I'll move the marker up and down, see where we're at. So looks like 21.090 for the 15 meter portion of the antenna. So that's pretty close. It's not too bad actually. It's probably very usable. And the 10 meter portion of the antenna is currently tuned to 28.30. Is that a zero? Sorry, 28.380, I think. I'm going to change the span here so that we're seeing more of what we really want. So let's start. We'll start our sweep at 19 megahertz. Why not? Okay, so that definitely changes the output a little bit for us to see a lot better. It's very sharp tuning. Oops, sorry. Very sharp tuning on the 10 meter portion. I mean, it's like pretty narrow. Still a good chunk of the 10 meter. So let's take a look at what the 10 meter is actually showing us. That's about a 1.4 to 1. So at 28.130,
we're at 1.4. Let's go over the hump to the other side. And at 28.460, we're also back up to 1.4, which is good. It means I can use that portion of the band from 28.1, basically 28.100 to 28, yeah, about 28.500. So fairly narrow there, but usable. And it's definitely tuned. So let's go look at the 15 meter side again. 15 meter is showing us on this side of the hump we're at 1.4 SWR, and the current value is 20.5. And on the other side, also at about 1.4, we're at 21.6 megahertz. So we're pretty close. If anything, I'd probably want to see this moved over. So the antenna is currently a little too long. We need to take about maybe a quarter, maybe a half inch off of both sides of the dipole and see where it moves to. But overall, I'm pretty good. Pretty satisfied with the this dual band antenna. It seems to be working correctly. I have a 10 meter portion that I can use. I might want to move that up a little bit, and to move it up again, you just shorten it. To move it down, you have to lengthen the dipoles. I have a 15 meter portion that's very usable as well. In 15 meters at the very center, I'm a 1.049 SWR, and that's currently centered at 21.090, so just shy of 21.1. I can move that up if I want to. I can move it down if I want to, just by lengthening and shortening the dipole. So yeah, I hope you guys enjoyed that dipole build using a 1-to-1 Balun choke built on a toroid. And if you have any questions, just leave some comments down below.